All right, so I want to talk real quickly about just the basics of linear regression, and then I'm going to hop over to Excel and I'll do a couple of examples with you there. But the basic idea is if you had this data set, somehow you've got your two different variables going on here, your x-axis and then your y-axis variable, and your data looks like this. You can see that somehow there seems to be a strong linear relationship, meaning I could draw a line through these, and it seems like the data is hovering around the line that I just drew. And so we'll use Excel to compute this line for us. I'm actually going to sketch an imaginary line here. I'm not actually computing anything, but the line of best fit would look something like, well, yeah, there it is. Something like that, let's say. And so the way that technology does this, it can be done by hand as well. It uses a method that's called least squares. Let me actually write that down. I lost my color that I like. There it is. So let's call this the linear regression is finding the line of best fit. And it's typically done using the method of least squares. I'm not even going to show you the formulas for this. We'll just use technology, and anything you'll do for your classes, you will use technology. But just to know what's happening, all that it's doing is it's imagining this line, and it's looking at the distance from each point to the line, taking that distance and basically squaring it and saying, hey, I want to find a line that makes the sum of all of these distances squared as small as possible. And you can use some techniques from Calculus 3 actually to figure out what the slope and the y-intercept of that line would be to minimize those distances. It's a classic optimization problem. So we'll leave that to Excel, but the point is you can see from this data that there is a line of best fit, and you can use Excel to do that, and I'll show you how. We, of course, are interested in the facts about this line. We're interested in its slope m, and we'll have Excel give that to us. We're interested in its y-intercept 0, b always, so Excel will actually tell us that this line is y equals mx plus b, and it'll give us those numbers. But there's really something else we're interested in as well, and that is how close does this data actually follow the line? And let me give you some examples. So look at that example that I drew. Let's draw another one where the data is somehow much more sporadic. Let's just say that it looks something like this. That was kind of a bad example, but maybe the line here looks somewhere down the middle, and you can just see at a glance here, somehow this data set seems much more closely huddled around the line. It's a better fit. It's much more correlated. There's a stronger correlation as the language that we're going to use than this situation. Actually, now that I look at it, this line was pretty good. But we can erase a data point there and maybe erase one here, and you can kind of imagine that. So that number that we're interested in, Excel will give this to us, is the number that is going to measure the strength of this fit. It's like a goodness of fit. And so that's called the correlation coefficient. And people usually denote it with R. And in the next video, I'll tell you just a couple of things about R, and then we're going to jump to Excel.